So, very good evening, students. How are you today? How's your evening going on? I hope you had your dinner already. Great, great, good. So, I've switched your proteomics courses to more basics now, not so much tough one. So, it will be more about now electrophoresis. Today, we will go through electrophoresis. And any questions you have so far about your career, where you want to pursue your PhD or MSc, how you want to do it, an MBA or something, you can feel free ask. We can have a QA fire question type now. Some question and answers we can have now. So you can ask any questions you have related to your career or something. I can share my story of my PhD, how I got my PhD. So basically, I was not a mediocre student, not so high-fi 90 percentile student, and so I got a chance to do my BTech in biotechnology from Singh College with 67% of percentage. But then I went for teaching in a government college in Punjab for 6 months. Then I left that job, and then I went for my master's in Germany in agrobiotechnology. So this was the place I went for my agrobiotechnology. If somebody is interested in career perspective, they can look for agrobiotechnology, which is taught in English. And then after my agrobiotechnology, um, I went for my master's in field of transgenic crops. So I was interested with the transgenic crops a lot, GMOs. Yeah, so I will answer to your questions. Let me just complete my story. Then after completing my master's in agrobiotechnology, um, the most of the people there in Germany, they were like burning the fields of the persons who were growing uh, GMO crops. So German itself, they like organic crops, they don't like GMOs. So they started to burning the fields. So I thought, let's switch my career. So I got a chance to work at Max Planck Institutes in Germany. These are the Max Planck Institutes. There I worked for my masters as in the institute for the field of um, cancer field. For the cancer field. And then after pursuing my masters, uh, I started to earn money with that, and I got opportunity to work for the master thesis also in the cancer field, which was paid one. So based on that, while working in Germany, I got a chance to work in Germany for my PhD. So within 3 months, I got a chance. I got a chance to work for my uh, PhD within 3 months because I did my master's in Germany. So I was preferred there. So I got my master thesis of 6 months there also because I was continuing my master's there from Germany. It's also. So that was the thing. So I got a scholarship also for my IRTG. So I was getting around 1.5 lakh to 2 lakh rupees per month for like 3 years, and which was quite a lot of money, which I saved also for my future. So that was a quite good investment to invest in my initially for my masters, then getting that money back out of from there. So that's what the beauty is of working outside of India. And moreover, you have I went for a lot of conferences outside of Germany, Italy, Gordon Research conferences, met many Nobel Prize winners, scientists, many professors. They were so frank and so nice to us that we cannot have the same level here in India. So that was the best part that I had experienced there. And moreover, the techniques, the methods that you want to pursue, you can have it far off the normal places there also. It's far way better than any other place. Europe, I felt Europe need to be the best place to work for. So if somebody is looking for in Europe some research part, so they can go through this link. DAD is a great link if you're looking for a master's or PhD. So I will share them in the and they are from Fraunhofer institutes also. They're also quite good one. Then if you're looking for a job or something in Europe, you're looking for some another university like King's College London for your masters, I will really appreciate that university for your studies. King's College London, one of the best universities in the world. And this is the place in under which I got my scholarship, IITG 1816. So these are the new students. We are in the past. So these are the various students who are working in the third cohort. So I was looking for myself. There I am. So, so you can also have a look over this. If you're looking for scholarship, and yeah. So your questions now. What is the best university to pursue MSc in biotechnology in abroad? I have preference in America and Europe. But if you have to want to save money, if you don't want to spend a lot of money, then I would suggest to go for Europe because you don't have to spend. It's all free. University will pay the fees for you. In America, you have to pay a lot of money before to start your career. So think about it before spending money. In India, there is a lot of scope at the moment. In the Ahmedabad side, in Gujarat side, Reliance have put up really big farms for the transgenic crops. So it's the best place to go for if you're looking for. So I shared some links to share go with the agrobiotech. Um, in India, it's ARI, Indian Agriculture Research Institutes. So you can look for in the Pusa also in Delhi. We have a very nice institute for agrobiotech. You can go for that. I would prefer to be, I mean, it's up to your choice whether you want to choose biotechnology or molecular biology because biotechnology is a field where um, it involves everything and molecular biology will be more specific then. So it's up to your choice how you want to go for. Molecular biology, you will be more into this lab specific. You will learn a lot of techniques there related to molecular biology and it will be more oriented to lab. But biotech would be more industrial oriented if you take as a MS in a biotech in biotechnology. So you can also pursue your life in the industrial base also, even though you can also pursue with the molecular biology, but you will be more on the lab focus, like academia base level. For USA, you have to crack, yes, for MS, you have to crack GRE, but for Europe, it's nothing like that. You just have to give simple IELTS or TOEFL. On based on that, you can get the admission. I would prefer Canada because in Canada, if you pursue your PhD, you can get your PR there, permanent residentship. But as compared to Germany, it's very hard to get a PR actually. So just think about that while choosing that. The scholarship program is more about you have to search on your own, like scholarship program within your own field, which field you are doing, and look for professors. I always recommend to everyone that look for professors where you can uh, help you uh, to find your suitable positions, what you're working on. All courses are taught in English in Germany. It's not in German, and I will prefer to learn some German at least to A2 level before going there. What is the average? But yeah, I studied so far for Germany. So oh, so average investments when I went there with my fees that I had money, I spent like I took two lakh rupees with me, 2 to 3 lakh rupees. So that's what I spent so far. But then I started to work from the 6 months onwards, and I started to pay my bills by myself. My house rent was around 250 euros per month. As a student, it was very cheap for us, and nothing like. Then our buses and train were free because of being student, and rest of the things are very cheap to handle there. But it's just you have to make money there. When you go there, you make money, and that will be converted into uh, so Germany versus Canada. The best part is I would say in Canada, if you pay for your fees, you can have the PR-ship easily. So in Canada, it's good. In Germany, if you go to Germany, you can have a life of European life. So there's a culture difference between Canadian culture and European culture. The European culture cannot be compared to the Canadian culture for sure, because you can travel around Italy, Netherlands, Spain, UK, all other places, Portugal, Poland. So all places are nearby. France. So that's the best part of doing in Germany. So all neighboring countries are quite nearby, and it's good to travel around. For microbiology, I would suggest, for my own experience, go to Canada. As in, there's a much future scope is more, language barriers are less, and you can have a better life there. What about the course? Do we have to give a separate exam for that before joining part from TOEFL? No, there is no separate exam. In some university, like if you go to LMU, then you have to give some special exams to get entrance. But most cases, it's not allowed. In Germany, it's everything is free, so it's all scholarship. So I would say it's the best place. Just check on the dart.com that I shared links with you today on WhatsApp. So there you can have a lot of scholarships there also. Marie Curie scholarship. Just look for the banks where you can have. No, there is no exam for PhD admission in Germany. Just look for the professor where you want to go for your studies. Then you can directly apply to a professor, which should be including your master thesis work together. So whatever you have done in your master thesis, that should be correlated with your PhD thesis. So both need to be correlated. So we will start just now. I was just having these sessions of Q&A. You have done your masters. Go for, I would not suggest go for PhD at the moment. Go for industry. Find a career in industry at the moment, and then start your career straightforwardly somewhere in the Bangalore or in pharma company or biotech company, and then Then slowly and slowly, gradually, while you are working, go for studying while you're working. So this will make a good companionship for both of you. You can earn money and you can maybe go for MBA later in your own field, or go for some master course later according to your studies, or industry could help you to learn more. So this is always possible. It's just about being good in the being valuable to your company. That's it. So if I have not any further questions, so shall we start with the electrophoresis of today's course? Okay. So today will be not a big session. It will be a small session because uh, um, because I was told that you want to learn basics and to cover the basics. So I just went through the basics now. So we are today we're gonna learn about various electrophoresis techniques. So, electrophoresis is a physical method of analysis which involves separation of compounds, um, that are capable of acquiring electric charge and conducting electrodes. So, it may be defined as a migration of charged particles through solutions under the influence of an external electric field. So this is divided into two parts: zone electrophoresis and moving boundary electrophoresis. So zone electrophoresis has four parts: paper electrophoresis, gel electrophoresis, thin layer electrophoresis, cellulose acetate electrophoresis. So out of all these three, mainly gel electrophoresis is important. And then out of moving boundary electrophoresis, capillary electrophoresis, isotachophosphoresis, isoelectric focusing, and immunoelectrophoresis. So these are the various four different electrophoresis techniques. So zone electrophoresis, first one, it involves the migration of the charged particles on the sporting media. So in the sporting media could be paper, cellulose acetate membrane, starch gel, polyacrylamide, and components are distributed onto the sport medium. Advantages are they are useful for the biochemical investigation, small quantity can be analyzed, cost is low, easily maintenance. And disadvantages are unsuitable for accurate mobility, isoelectric point determinations, and due to the presence of sporting medium, technical complications such as capillary flow, electroosmosis, absorption, molecular sievings are introduced into them. So general methods of operation: saturation of media with buffer, media with the buffer sample applications, electrophoretic separations, removal of the sporting media. The instrumentations that we required is electrophoretic chamber, electrodes, diffusion barriers, supporting stabilizing media. So we required all these things there. So paper electrophoresis, it's in this you have one electrode, you have a battery of 45 volt DC battery, you have a positive electrode, you have a negative side, and then you have horizontal paper on there, and then horizontal paper, it could be now horizontal or vertical electrophoresis. So in horizontal and both in vertical you have a airtight housing, and there is a filter paper strip is there, then there's electrodes on the sides, and then you have a filter paper horizontal in the horizontal paper electrophoresis, in the vertical is on the top. That's the main difference. Then filter paper such as Wattman number 1, And Wattman number 3 millimeter of strips are used of 3 to 5 centimeter wide, which has a good effect, and separations takes place in 12 to 14 hours. Advantages are it is economical, easy to use, and disadvantages is again electroosmosis and inorganic components and absorptive properties of parents doesn't allow the proper formation of bands. Now comes the gel electrophoresis is brought through the molecular sieving technique based on the molecular size of substances. So gel materials such as molecular sieve are used in them. So gel is a colloid in the solid form in this case. It is important that the sport media is electrically neutral, and definitive types of gels which can be used are used in this case. So like agar and agarose gel stretch, acrylamide gels. A porous gel act as a sieve by retarding or in some cases by completely obstructing the development movement of macromolecules while allowing smaller molecules to migrate freely. So here you have a casting tray in which you add your agarose solution, then you add comb on top, then there is a hole in it, then you add your sample, then you attach to your power supply with positive and negative, and then you run your gel. So these could be vertical and horizontal itself also. And what is the difference between agar and agarose? So agar is a mixture of polysaccharide extracted from seaweeds, and agarose is a highly purified charged polysaccharide derived from agar. And agarose is a chemically based disaccharide repeating units of 3,6 anhydro L-galactose. And agarose gels are fragile and they're usually hydrocolloids, and they're held together by the formation of weak hydrogen and hydrophobic bonds. They are widely used in the immunoelectrophoresis. So in the solid states, they looks like this. At the temperature of 45 degrees Celsius, initially gels looks like this. Then after the aging, they go into this shape. Again, if you make them 100 degrees Celsius, they could come into the back same shape. So some video about agro.
This video will take you through the process for loading and running DNA samples on an agarose gel. You will be using a mini subcell to perform agarose gel electrophoresis. The subcell has an electrode wire running across the bottom of each end. This provides for an electric current to pass, which separates the DNA fragments in the samples. First, align the gel so that the wells are closest to the negative or black electrode. DNA is negatively charged and will move from the negative electrode through the gel toward the positive or red electrode. Place the agarose gel into the gel chamber. Add electrophoresis running buffer to the reservoirs at each end of the gel chamber, and keep adding buffer until the wells in the gel are covered by at least 2 millimeters of buffer. Place your samples to be loaded in the correct order according to the lanes they are assigned to be run in. Check your lab protocol for this information. To obtain a DNA sample, slowly depress the plunger on your adjustable micropipette to the first or soft stop. Holding the plunger down, insert the tip of the pipette into the microtube with the DNA sample. Place the tip close to the bottom of the sample, then slowly release the plunger button. When loading the samples, keep the pipette tip perpendicular to the row of wells. This will reduce the risk of accidentally puncturing the wells with the tip. Lower the tip of the pipette until it breaks the surface of the buffer and is located just above or just inside the well. Slowly apply pressure to the plunger button and observe as the sample fills the well. Make certain you stop at the first stop on the pipette, pause, then slowly remove the pipette while keeping your thumb down on the plunger. Once all the samples have been loaded, avoid any bumping or movement of the gel chamber. This might result in the samples spilling into adjacent wells. Place the lid on the gel chamber with the terminals correctly positioned to the matching electrodes on the gel chamber, black to black and red to red. Connect the electrodes to the power supply, again making certain the electrodes match the terminals on the power supply, red to red and black to black. Switch the power supply on, then set the correct constant voltage for running the samples. See your lab protocol for this information. If a timer is available on your power supply, set the clock for the proper time for your run. Press the start button to begin the flow of current that will separate the DNA fragments. At this point, you should be able to see bubbles coming from the wires at each end of the gel box. Notice that the positive or red electrode has fewer bubbles than the negative or black electrode. In a few minutes, you should see the samples begin to migrate from the wells into the gel. Notice as your DNA samples run, the dye front moves from the negative electrode towards the positive electrode.
So that's how you run your your gel, agarose gel, the technique. So now comes the next polyacrylamide gel electrophoresis. It is prepared by the polymerizing acrylamide monomers in the presence of methylene bis acrylamide to cross-link the monomers. So structure of acrylamide looks like this. So structure of acrylamide CH2, CH, CONH2. So here on the right hand side, but when they make together, they make covalent cross links like this, and then you can have your desired results. So proteins are separated on the basis of charge to mass ratio and molecular size, and phenomena called molecular sieving. So there are two types of pages, native page and denatured page. So native page is the page that runs in the non-reducing condition so that the analyte's natural structure is maintained. So separation is based upon charge, size and shape of macromolecules, and this was original mode of electrophoresis. And denatured page or SDS page, separation is based upon the molecular weight of the proteins, commonly method for determining molecular weights of proteins, and very useful for checking purity of proteins. So to check on the page procedure, I will take you to one nice video of a lady which will explain you how SDS stacking gel and separating gel have glycine, chlorine and protein, how because of their chemical nature we have a different flow of protein. So we will understand basically the pH behind the SDS page, how SDS and beta mercaptanol are breaking the covalent bonds and disulfide bridges respectively. So that's what this video is all about. So I will start this one.
SDS page, sodium dodecyl sulfate, polyacrylamide gel electrophoresis. So I'll speak about several points. First, what is SDS page, the sample preparation, the discontinuous gel system, and the separation principle. So at the end of this video, you will get a very good idea about SDS page. You will understand everything about the principle and the technique. So I'll start first talking about what is SDS page. SDS page is an electrophoresis technique. It's used for protein separation, and the gel used for SDS is polyacrylamide gel. Acrylamide is an inert material, so it doesn't interact with the proteins, which is a good feature, and it forms a matrix. The pore size of the matrix can be determined by the concentration of the polyacrylamide gel, so it's a good gel. The SDS gel is composed of two layers of the gel. The first is the stacking gel. The second is the separating gel. In the stacking gel, we have the wells in which we apply the protein samples, like here. And then we apply an electrical field to the gel, going from negative on the top to positive on the bottom. The electrical field is applied by a battery. And when the electrical field is applied, the proteins start to migrate from negative to positive, and they are separated in the separating gel according to their, like this, according to their molecular weight. This is the general description, but I'm going to speak about everything in details. First of all, to understand the principle of the SDS page, we should speak about the sample preparation. In the sample, we have the proteins, and we also have what we call the denaturation buffer, or the sample buffer, or the Lamley buffer, which is composed of several substances or materials. And the most important two materials of this is SDS and the beta-mercaptoethanol. So I'm going to speak about them first. SDS is an anionic detergent. It has a polar side and a non-polar side, a polar side and a non-polar side. When SDS is dissolved, it gives a negative ions, and these SDS ions bind to the proteins on the side chain of the amino acids that in the protein. So SDS gives the protein a negative charge. Whatever is the original charge of the protein, even if the protein is originally negative or positive or neutral, the SDS gives the protein negative charge. The SDS also denaturates the protein. So it converts the protein from its tertiary and secondary structure to its primary structure by breaking the bonds that are implicated in the formation of the tertiary and secondary structure. Similarly, beta-mercaptoethanol also has a role in the denaturation of the protein. It's a reducing agent. It reduces the disulfide bond in the protein, so it separates the subunits of a certain protein. So this is the protein. This is the amino acid or the peptide chain of the protein, and then the secondary and tertiary and quaternary structures are formed by non-covalent bonds like the ionic bond, the hydrophobic interaction like van der Waals bonds, the hydrogen bonds, and the disulfide linkage. And these bonds are broken by the SDS and the beta-mercaptoethanol. At the end, we will have the protein as a peptide chain. So the shape of the protein doesn't play a role in the SDS, and also the charge of the protein. So neither the shape nor the charge of the protein plays a role in the SDS page, only the molecular weight of the protein. So this is SDS and beta-mercaptoethanol. We also have the tris hydrochloride, which is a buffer that is of pH 6.8. It also gives the chloride ions. The chloride ions are also important in the mechanism of SDS. I'm going to speak about them. Bromoethanol blue is a staining dye. It's used to give the sample a blue color, so we can detect the sample on the gel, the level of the sample on the gel. Glycerol increases slightly the viscosity of the sample. And also we use distilled water to continue the volume, and we use distilled water because we don't need ions in the sample. Now I'm going to speak about the discontinuous gel system. So we have two layers of the gel, as I said previously, the stacking gel and the separating gel. And they have different pH. So the stacking gel has a pH of 6.8. The separating gel has a pH of 8.8. We also have the two electrodes that have pH of 8.3. There is something called the migration buffer, and the migration buffer contains tris and glycine. Glycine is also very important in SDS page, so I'm going to speak about glycine. Glycine is an amino acid, and it's the simplest amino acid because the side chain is only a hydrogen, and it's a zwitterion. What does that mean? It means that in acidic pH, so below 2.3, this amino acid is protonated, so it's positively charged. And in basic pH, over 9.6, it's negatively charged because it's deprotonated. Between these two values, which we call pKa1 and pKa2, this amino acid is neutral. And it's totally and exactly neutral in the very middle point between pKa1 and pKa2. So how can we know it? We take the 2.3 plus 9.6 divided by 2. So we get the value of 5.95, which we call the isoelectric point. In the isoelectric point, the molecule is exactly neutral. Above this point, so at pH, let's say pH 6 or pH 6.5, the proteins start to be slightly negative, and the negativity of the protein increases gradually between 5.95 and 9.6. So we should know that in this area it's slightly negative, and the negativity increases. So let's see. When the pH is in the electrode, the pH is 8.3, and then glycine is negatively charged. As you see here, glycine here at 8.3 is negatively charged. So the glycine will migrate from the negative towards the positive pole because it's negatively charged. But when it enters the stacking gel, in which the pH is 6.8, the negativity of the glycine decreases, and then the mobility of the glycine becomes so slow. So I will speak about each one of these separately. So let's first take the stacking gel. In the stacking gel, the pH is 6.8, and here we have the sample. So in the sample, we have chloride ions. As I told you, we have the tris hydrochloride, which gives chloride ions. We have the protein SDS complex, which is negative. Chloride is also negative. And we have the glycine, which is at pH 6.8, neutral to slightly negative. So they migrate in this order. So first we have the chloride, then we have the protein, then the slowest is the glycine. So as you see here, the proteins are stacked between the chloride and the glycine. And because of this, we call this the stacking gel, because the proteins are stacked between these two. And when the three molecules reach this line, they start the separating gel. In the separating gel, the pH is 8.8. This is the separating gel, and the pH is 8.8. So the migration takes place in this order. So first we have the chloride, which migrates so fast toward the positive charge. Then we have the glycine, because when the pH is 8.8, the glycine is much more negative, and so it becomes faster than the proteins. And then we have the proteins. So you see here the proteins are left free behind. So the proteins are free behind, there is nothing, and then they are separated freely in the gel. The question is, why do we have this discontinuous gel system? And the answer is, when we apply the sample in the well, the sample is about 3 or 5 millimeters. And then the proteins will not be applied to the gel at the same time. So if the separating gel starts from here, the proteins will be applied to the gel not at the same time. But when the proteins are in the stacking gel, they are stacked together and then they enter to the separating gel at the same time. And they are separated to give the bands, especially like when proteins have the same molecular weight, they should migrate together at the same time to give this band. Now, the separation takes place because this gel is a matrix, as I said before. So you can imagine it like this. This is the polyacrylamide matrix. This is the sample. So the sample migrates from negative to positive. And when it starts in the separating gel, the large proteins cannot migrate farther because they stick in the gel earlier. I should say that the stacking gel is a very low concentration of polyacrylamide, and because of this, the proteins do not stick in the stacking gel because it's so diluted. It's not concentrated, so the pore size is so big. But in the separating gel, the separating gel is more concentrated, and so the proteins will stick at a certain point. So the larger proteins stick earlier, but the smaller proteins migrate and stick later. And then we will get bands, different bands of different sizes of the proteins. This was everything I wanted to tell you about SDS page. I hope you enjoyed this video.
So that was about SDS page, students. So I will share this link with you. Oh, somebody just subscribe. Please, students, subscribe to the channel. It will really help me to run my YouTube channel for future onwards. It's still very far away from my dreams, but it has been started just because of you students. So if you have not subscribed so far, please subscribe. So let's continue with the SDS page. So we have studied about in detailed manner how SDS page is done in a very succinct manner. So I will not go through these fields again. So here we can see that we have a denature. Oops. So we have a denature sample with the sodium disulfate SDS. So SDS is a detergent that binds a stoichiometry to the number of peptide bonds, thus separate on basis of size, molecular weight, and then so they place mixture of proteins on gel, apply electric field. So they are partially separated proteins, cross-linked polyacrylamide gels, and direction migrations. So you can separate your particles with the large, middle, and small like this. So we have done with there are two types of vertical and horizontal, and there is a pulse field gel electrophoresis, which is a in the pulse field gel electrophoresis. It's a technique used for separation of large DNA molecules by applying to gel matrix an electric field that periodically changes directions. However, with periodic changing of field direction, the various length of DNA react to the change at the different rates. The voltage is periodically switched among three directions. One is in the central axis, then at the angle of 60 degrees Celsius, either sides. So like one on this angle and one on this angle, one on this angle. So like this you have two different angles in this case. Then comes your next thin layer electrophoresis. Studies can be carried out in the thin layer of silica, Kaisguer alumina. So less time consuming, good resolution is observed in this. Widely used in the combined electrophoretic chromatography, studies in two-dimensional studies of proteins and nucleic acid hydroxylates. And then comes the cellulose acetate electrophoresis. These are all coming under your zone electrophoresis. So it contains 2 to 3 group per glucose unit, and its absorption capacity is less than that of paper. It gives sharper bands, provides a good background for staining glycoproteins. It is being used for the big biological protein samples like albumin globulins, alternative to paper electrophoresis. Then comes the boundary electrophoresis. The moving boundary electrophoresis methods allows you to charge species to migrate in a free moving solutions without supporting the medium. So they consist of U-shaped glass cell of rectangular cross sections with electrodes placed on each of the two limbs of the cells. And sample solution is introduced at the bottom or through the side arm, and apparatus is placed in the constant temperature bath at 40 degrees Celsius. And then detection is done by the measuring the refractive indexing through the solutions. So like here we can see in the diagrams. So their applications are homogeneity of macromolecules, analysis of complex biological mixtures. So these are all possible because of this. Now comes the next, capillary electrophoresis. This is mainly based on the charged particles towards the opposite poles, separate from each other based on the physical characteristics. So capillary electrophoresis has grown to become a collection of a range of separation techniques which involve the application of high voltage across buffer fill to achieve separations. So capillary electrophoresis then is a technique of performing electrophoresis in buffer fill narrow bore capillaries, normally around 25 to 100 millimeter in diameter. So here you have a capillary electrophoresis method shown here. That is, just a second. Uh, you have your all protein samples here at the cathode initially. Then you run your electrophoresis like this. Then you have a node buffer on the other side, and then you have a photocathode on there which collects the data in the computer, and you can see the absorption versus time readout of your electrophoresis. So then comes the next part, isotech In the isotech development of the potential gradient. So in this based on the moving boundary electrophoresis, leading electrolyte with a higher mobility than analytes, and a trailing electrolytes with a low mobility are used, where the separation by isoelectric focusing depends upon the existing of a pH gradient in the system. The technique of isotechphoresis mainly depend upon the development of a potential gradient. So in this example here we can see three particles A, B, C, a charge are being separated and pro-concentrated via electrophoresis. So after the separation is conducted, all the particles move at constant speed. So that is known as isotechphoresis. Then comes next your immunoelectrophoresis. In this, your antigen and antibody on antigen antibody reactions, your electric potential is applied to that. That is known as immunoelectrophoresis. The antibody are electrophoretically separated, antigen diffused towards each other, resulting in the precipitin arcs where antigen antibody complexes forms. And this technique has been referred to as immunoelectrophoresis. Antibodies placed in trough cut parallel to the direction of electrophoresis and run the electrophoresis. As a result of precipitin arcs will be formed due to antibody and antigen complex formation. So then comes isoelectrofocusing. We did this in detailed manner yesterday, so I will not continue with this. And also two-dimensional gel, we did this also in quite detailed manner. So any questions for the students? So thank you very much for today's lectures. So I will take you now to from this um to the to my presentations of my work, what I did in my PhD. So related to your SDS page gels, so something related to that, we can continue now with that page, that part. So if you have any other questions, so this is one small cartoon that I found from the restriction enzymes. So that was the last year DNA invited the restriction enzymes to the Halloween party. So great costume. So he comes to cut the DNA. So nobody knows why he's in that costume. So some silly jokes. So I will share the protocol also with you. So just want to touch some part like how this SDS page has helped me during my PhD time. So I will share that part now. So from here. So here before, I mean, this is a way to how to give your thesis, your master thesis or a PhD thesis. So this is my PhD thesis presentations. So first you have to explain your hypothesis, what you why you are concerned with that. So to in order to do so, let's have a look at the ER signaling pathway method. So there's a PERK protein which get dimerized and phosphorylized both together. So become two PERK proteins with phosphorylation, and then there's a kinase activity is happening leading to the ELF2 alpha phosphorylation. ELF2 alpha is phosphorylated leading to the either stoppage of translation and production of ETF4, and with the help of CHOP protein they do the transcription folding enzymes upregulations. So they deal with all these paths. Whereas RE1 alpha is also get dimerized and phosphorylate, leading to the RNA splicing of XBP1 protein and having a translation of XBP1 and having these all these functions again. And whereas ATF6 alpha it's get migrated to Golgi body, from Golgi body it's got spliced S1P by S2P, and then after cleavage ATF6 is being put in the nucleus. So our task was to check the protein CTGF, whether is it any connection between ES stress, because ES stress is there, all these mechanisms are started to happen. So we want to check a comparison between CTGF and these proteins. So how can this Western blotting or SDS page could help us in these techniques? So first we have to check the CTGF structure, how the CTGF structures looks like. So it is based on the four different motifs, that is IGF, TGF beta, VGF and VGF. So N domain and C domain. So we want to check hypothesis, that is CTGF affected by redox or ES stress in cardiomyocytes, or is ES stress and UPR pathway affected by the expression of CTGF. So the heart samples were put up, and then their values were checked with the ischemic cardiomyopathy and dilated cardiomyopathy. The dilated cardiomyopathy, we saw that there is an increased concentration of CTGF. So that proves that the CTGF is cysteine dysregulated in heart disease. So whosoever has a heart disease, they have this protein in high amount. And this is the main thing that I want to show you. So you, whatever you do experiments, you do either concentration and time dependent. On the left side, they are the time dependent experiments on top here also, and this is a concentration dependent experiment. So by adding H2O2 for 3, 6, 10, 15, 30 minutes, we saw a gradual increase in CTGF structure with tubulin as a control. And also we check at that hours, 2, 4, 6 hours, we saw an increase in that also. But with increase in DDTs, then there is a two types of SDS pages I did here. One is non-reducing and reducing conditions. So non-reducing conditions, in your lamellae buffer, when you're preparing your samples, you just don't add EDT. Another case you add DDT. So in this case you see this ladder shape, very nice ladder shape in time dependent and also in concentration dependent. So that's how you can check the differences of various concentration and time dependent differences things. Then I check with various reagents which cause ES stress in the protein uh, in the cell. So like thopsigargin and tunicamycin are the one which are creating ES stress, and then I check all the others markers which are the ES stress markers and also CTGF markers. So I saw that at 6 hours CTGF was increased with the use of thopsigargin, and also with tunicamycin I didn't see much changes actually. And with the heat shock protein, I also saw the decrease in the CTGF expression. That means that heat shock is also related to the CTGF expression. Then I check pH, Mg132, BFA, all these things with respect to CTGF expression, so I didn't saw much changes in that. Then effect of siRNA, CTGF knockdown and NRCM at mRNA level. So XBP1 is spliced in the case of a knockdown version. So that means that CTGF is dependent upon ES stress also. Here also with a decrease with siRNA knockdown of in the cells of CTGF, I saw other markers to be decreased. So that proves that there is a correlation between ES stress and CTGF also. Then there is a EATF6 alpha in the knockdown versions. We saw them to be nucleus. Otherwise, they are present at the outside of your nucleus. So that's also proof that there is a correlation between ATF6 and CTGF also. So I can confirm that oxidizing agent, ES stress reducing agent, ES stress markers, heat shock proteins, HSP47, and end stage heart failure. So they're all responsible for CTGF, but whereas pH, Mg132, BF, that doesn't have much role on it. So like this, you show your one nice diagram, then you show all your conclusions of it, what things that you are, and future perspective. Then you thanks to all your people. And then this was one paper from my first research that I did. It's published in the scientific reports in Nature. The redox activity of PP1 alpha under redox stress condition, consequence of glutathione mediated uh, things. So thank you very much, students, for today. So I think I want to keep it short and crisp with this electrophoresis, not in details. So you have some questions. Sir, I have a question. So I am currently writing a paper on biotech use in vaccine development. Is it in purpose antigen synthesis via vector plasmid? In it, I propose an antigen synthesis via vector plasmid. I wrote that we could create large number of antigens separate from bacteria with gel electrophoresis. Will it work? I want to know how can I separate large quantity of antigens from bacteria. Oh, large quantity of antigens. Let me Google this. That's the best part to answer many of our life because I'm not into this bacteria field. I never studied them. So if anybody knows about them, please answer it. Separate large quantity of antigens. So there's one paper, uh, micro machines. Continuous flow separation of foodborne bacteria from large volume. Ah, this is something else, not related to your field. Sorry, bro. Cannot answer. Uh, I didn't get why I need to different gel stacking separations. Can you explain that part again? Because of the pH, bache. The pH is the thing. So initially we have pH 6.8, then pH 8.7. So we keep a different pH so that the separation of a molecule it goes in continuous manner, in smooth manner. Different running of separation protein esters and the influence. Importance of running buffer in separation of proteins. So they are helping the providing the charge ions, bache, all the charge that they required, and this continuous smooth flow for it. This is I know so far. So any further questions, students, related to electrophoresis? So we are done with it today. So review date is 20th of October, and so far just get into a group so you can make a 3 to 4 people group, because I have zillions of people who did last time we had a workshop, and everyone did it on their own. They were very nice students actually. You're also all nice students. You never complain about anything. Um, so where it is? So assignments. So I got lot of, even still a lot of in my emails now. So these all people did their own with creating a group. So please go with it. And once you submit your certificate, your assignment, then you will get the training certificate uh, for your work. So please work hard for it, and start studying for the same. So any further questions? Anything else you want to ask, students? Can we get industrial field if I'm from microbial field? Yes, yes, you can. Why not? Can we manage living costs through internship in Germany? Yes, it is possible. I did it like that. Through internship, I was paid 400 euros, and I was also working sidewise. So I did together, and I was able to do so. Okay, then, if you have no other questions, thank you very much. Uh, and good night. Then see us tomorrow, same time, same place, with more data and more interesting studies. Yeah, all good, all good. Yes, yes, you're all good students. So we are trying our best to teach you the best level and try to make it simple so that it don't get complicated. So that's what I'm trying at the moment. So I want to take you to the advanced topics soon. Let's see if we are able to understand these, then we go for the advanced topics. Okay, students, then I will leave you now. Thank you so much. Good night. Bye bye.